Good morning. Actually, good afternoon for you. So, okay, basically, do I have a little bit more time than my usual time then?
Yeah, you can.
Okay, perfect. Then I don't have to rush through a lot of material. Okay, thank you for the kind invitation. So what I will be talking today is nanophotonic bioelectronics. In other words, we are trying to do electrophysiology using nanophotonics. And this particular slide is basically like the grand goal. Obviously, I'm not going to show you a single fiber carrying all all sorts of information that you need from brain. But I just want to give you an idea how to say the limits of this technology. So if you think about the human brain, there is like 86 billion neurons, and these are spiking at 200 times at a rate like 200 times per second. So if you calculate the amount of information generated, it's somewhere like 17.2 terabytes per second. And you would say, this is a huge amount of information, obviously, right? If you were to try to put that into a hard disk, it will be full within a matter of seconds. Obviously, it's very difficult to carry this much information using non-optical wiring, like electronic wiring, right? If you think about optical fibers, though, an optical fiber can carry 1 billion-fold more information than a simple copper wire, an electronic wire, right? And if you look at actually a short one, a relatively short one, even with today's technologies, you can actually carry 1 to 10 terabytes of information within 1 to 2 meters long. This is just a big if. If you wanted to, carry every neuron's information through a fiber, without much struggle, you should be able to do that. With a little bit of technical improvements, even with the existing commercial technology, you should be able to carry every neuron's information using a fiber, at least for a short distance. And these are typically, few meters is what you will need if you are trying to create some kind of a therapeutic device. Obviously, you don't have to monitor every neuron. You look at local field potentials. Often these are like a collection of neurons. In other words, basically, you are very capable of carrying huge amount of information, carrying a highway between human brain and the outside world, which they refer as commonly, brain and machine interfaces or brain computer interfaces. So you basically ceiling is up there, you can do, whatever you want to do using optical technology. The problem though, how do you convert electrophysiological signals into electronic ones? So let me give you a brief idea. What is the current technology? And I will show the differences and the advantages and how our system works. And I'll give you some very interesting results. So this particular guy here is actually one of my collaborators' images, which shows this thing called microelectrode arrays. These are like microelectrodes. And you can see how large a cell looks like. It's almost comparable. I mean, these microelectrodes are actually a little bit larger than cells. So these are basically routinely used stuff in any electrophysiology lab. They are like the workhorses of the electrophysiology labs. These electrodes, basically gold electrodes that are coated with something called PDOT, a polymer material that helps matching the impedance between the solution and the metal electrode. So it kind of improves the the electronic connection in between. But just to remind you, this is important because we're going to come back to gold and PDOT later, but using in a completely different way. So here, gold is used to measure electrical changes or capacitive accumulation on the surfaces, and you use another electrode to find the potential difference. You need a reference electrode, so on and so forth. But overall, this is the device, and then one of the main limitations of these things, as you can see here, you cannot pinpoint which neuron you are getting signals directly from. It's a little bit tough when you have such a low pixelation density. The cells accumulate or culture the way they like, not the way you put the electrodes in. As a result, it's a little bit difficult to measure individual cell connections. Also, you have to wire these things. That's another problem. Obviously, every time I make a measurement here, I have to take this guy all the way to the external circuit, which does the processing. So that's not actually a very good thing, right? So what people did, they developed more recently something called high density microelectrode arrays. For these guys actually are based on CMOS. So I'm not putting that picture here because I'm going to use this later, but they use CMOS technology. And, when you use CMOS technology, the first impression is, if I have CMOS and, CMOS can be, transistors could be very small, right? They make this transistors that are only like tens of nanometers in size, even if you were to incorporate contacts. These are extremely small devices. But then one problem with the high density microelectrode arrays is that you have to process the information on chip where you take the data. You have to take that analog signal, turn into a digital signal, amplify it, so on and so forth. So you need to do on-chip conditioning so that, you want to go tens of thousands measurements, then you do not have extremely complex, my apologies, external or backend processing. So you want to make sure that the data is processed here. So you can use actually these wires at the end of the day, you need less resources outside to be able to read that information. But then you have to do on-chip condition. So that's how we actually move from this low density, a few hundred at most electrodes to thousands, and most recently tens of thousands of electrode measurements over a chip. But to do that, you need front-end amplifiers, so on and so forth. When you put those guys in, then your individual pixels are again becomes big. They are like 25 micrometer square footprint. I mean, the technology is very good. You have tens of thousands electrodes, at least in the best case scenarios, but then you still have this pixelation density problem. So these are basically most recent numbers that I'm giving you here. So, the state of art is like you can maybe do 65,000 electrode measurements. These are not one at a time. Basically, often what people do, they gate it, time gate it, because they have to share the resources. They run out of bottleneck with the resources. So they kind of time gate it. They look at, 10,000 of the electrodes and then next 10,000, so on and so forth. Obviously, the many you can gate depends on how quickly these signals are being created by the cells. In other words, how fast they're spiking in, as a result, you end up getting basically certain limitations with how many cells you can monitor individual times. So what we did is actually the part I want to show you. This cell, if you look at closely, in the case of our systems, our electrodes looks like whatever is in the background here. This is an SCM image, this is an optical microscope image. So if you look at this SCM image closely, you can see there's a periodic pattern behind. And that periodic pattern is our nano antenna. So what we do, we use nanoscale antenna that are sensitive to voltage changes and then generate an optical signal. Obviously, this is not trivial. I mean, people have used antennas for many purposes, fluorescent signal enhancement, label-free detection. There are many applications outside the biological things as well, like, monitoring electrochemical reactions, so on and so forth. But, detecting electric field is not so trivial. And I will show you how to do that. But just to remind you the differences between these two technologies. First of all, individual footprint of these devices are extremely small. They are 0.01 micrometer square. And we are only limited by the diffraction limit of light. And when you look at it, there are no wiring required. Obviously, we are coming with light, collimated light, and we collect it using a CCD. So you can actually project it from a surface to another surface. So you can take advantage of photonic properties, no wiring requirements. So you solve with a single change of technology, you solve one of the major problems in the field, that is the wiring issue. And our electrodes measure extracellular potential. That's an important thing. I will come back to this later. So we are not actually implanting these electrodes into the cells. We are not opening pores. These are just like microelectrode arrays. The cells land on it or cells reasonably away from it. It can actually measure the signal. Now, our electrodes are made out of gold because these are plasmonic particles. Gold is a good material for plasmonics. And we actually load them with PDOT material, PDOT PSS being specific. And in a way, material-wise, it's identical to these electrodes. But it's 100,000-fold smaller version. If you think about it, it's like a gold, coated with PDOT is the electrode people use. Our electrodes are 100,000 times smaller of them. Material-wise is identical. It uses gold, not for electronics, but plasmonics. It uses PDOT, not for coupling electronics, but generating an electronic to optical transition or acting like a mediator in between two physical domains. Now, using this, actually, I will show you, we can multiplex things, you know, and this is actually experimental show. We multiplex things up to, or the values I will show you is basically 22 million probes. And this number could be significantly higher, and I will show you why. And when you look at electrode density too, it's 3 million electrodes per millimeter square. So the advantage of this, you know, when you project this, you can see subcellular signatures, because you see, I have thousands of this, my apologies, I have thousands of this laying underneath the cell. So when I actually look at individual wires or a group of, you know, nano-antennas, I can actually tell exactly where I'm measuring signal, unlike these electrodes. So I can actually, you know, resolve subcellular signatures. We haven't started doing that, but, you know, it shows that we can actually resolve synaptic connections. The resolution is that high. And let me give you an idea what the existing technology looks like. This is a pretty good diagram summarizing what is out there. The first generation technologies can measure 16 measurements at a time. Obviously, you know, electrode density can be varied with the sensing area, but it stays more or less on this curve. You know, the next generation was 256. You know, a lot of people use these things in the lab because they're, you know, economically feasible. I mean, they're cost efficient. And then, you know, the state of art, as I was referring, they're like 65,000. So our wireless electroplasmonic nanoelectrodes, so that's the term I started using after my, you know, couple of talks within the community. I realized the, you know, major issues these people are having is to do with the wiring. So we start using this term wireless because that actually solves one of the most important problems in the field. But in addition to that, if you look at the electrode densities, you know, the best ones you will see in you know, existing technologies, they're not going to be more than, you know, 20,000 at best electrodes per millimeter square. So we are on the order of 3 million. And I don't think that you can improve this electrode density significantly with the existing technology, because you're already running to the physical limits of existing, you know, CMOS technology, in other words. They're already as small as they can get. They can get maybe a little bit smaller, but you're not going to improve this thing an order of magnitude. So right here, we're actually orders of magnitude better than that. We can do large area measurements. We show that actually we do these area measurements, but we are limited by the existing cameras or the cameras in my lab. If you were to actually connect a larger CCD, you can make this area significantly larger. So it actually scales easily because you see, every time you want to scale the existing technology, you have to do a lot of rewiring and processing advancements. So it's very difficult to move the existing technology to a higher multiplexing capability so that, you know, you can see a large network of cells interacting with each other, so on and so forth. So it's difficult basically to achieve that. And this graph actually is a very good graph, the difference between, you know, integrated technologies like, you know, digital technologies versus analog. So if you look at actually Moore's law, you know, since 1970s, you know, the transistor count doubles every 1.5 years. And, you know, we started with somewhere tens of thousands, and then we are somewhere tens of billions now. So it obviously improved significantly. If you were to look at microelectrode array technologies, starting with gold electrodes and now with the CMOS technology, it stays on another curve, which doubles every 7.4 years. Obviously, you know, although this factor looks like a factor of, you know, 5, it makes a huge difference. You know, the best technologies that exist today, I would say, you know, there are some thousands at best. So this is a little bit older graph, I believe. I forgot to put the reference number for this, but it's well established fact that, you know, you are going to have difficult time really reaching the limits of the CMOS technology. Now, what I will show you today is a quantum leap, literally. Basically, we move from a multiplexing capability down here all the way up here. And you started to catch basically, you know, CMOS scaling technology. Now, the question is how to read electrophysiological signals optically. And, you know, this has been the goal of scientists more than half a century, starting early 60s, early 50s, actually. People started to actually do experiments with this, you know, voltage sensitive dyes. Now these guys work in a way that this is like a protein attached to a fluorescent molecule. The protein folding changes when there is a large electric field. In the case of a membrane, obviously, the potential difference between inside the cell and outside the cell is like 100 millivolts. It's a small number, but that, drop occurs in this, 5 nanometer thick cell membrane. It creates a huge electric field, right? Obviously, that electric field is going to lead to a change in the protein structure, which leads to change in the fluorescence signal level. So people use this with the hope that, these are molecules, so you should have, high resolution measurement capability, only limited by diffraction limit. One problem though, in order to put these proteins into the membrane, you have to do some genetic modification or use viruses to deliver these things. So this is obviously problematic. You cannot work with humans. There are other problems whenever you use fluorescence, you are going to have problem with phototoxicity, especially you have to incorporate so many of these things in there so that you get a sizable signal, but that, perturbs the membrane behavior. Also, you can have bleaching problems because often the signal is weak. You have to blast it with large number of high intensity light, which actually creates bleaching problems. The reason for that is basically, this is a fluorescence molecule. I mean, it's a small thing that has only a cross section of 10 to the power minus 2 nanometer. And often these particular voltage sensitive fluorescence molecules have cross section, quantum yields that are extremely small. These are much smaller than the typical fluorescence molecules you use for, in assay applications. As a result, people often use this very high intensity light. 3 to 12 watt per millimeter square. Obviously, you cannot continuously expose these guys with this light because it will burn your cells in a matter of seconds. So what you do, they just chop it. They occasionally open it, close it, open it, close it. Obviously, that creates another problem. How do you know when the cells are spiking, how they overlap? So obviously, the practical implications of this is large. And what often people do, in order to get a sizable amount of signal, they actually don't look at single fluorescence molecules or a group of them. They look at a large chunk of them. Often, like you have 1 million fluorescence molecules in a cell, and then in order to get a good signal to shot noise ratio, you actually image 12 cells at a time in a region. So it becomes actually, even then, you are on the order of tens SSNR ratios. And another approach people did, some people actually in the laboratory showed you can detect signals at the subcellular resolution, but it's a little bit of a trick because you cannot obviously image these things in real time. So what they do, they stimulate this thing 200 times at the exact given intervals, and then they image it in over 200 periods, and then they kind of able to get enough signal so they can start looking local stuff. Obviously, its practical implications are minimal. For solving biological problems. So some people come up with these newer ideas. They are like, okay, the fluorescence molecules cross sections are so small. Why don't we use fluorescence quantum dots? These guys' cross sections are 100-fold better. These guys basically field sensitive. It uses quantum Stark effect. Wave function overlap between the holes and the electrons vary. As a result, this transition rate or between these two quantum states vary. As a result, you end up getting a varying coupling strength, changing intensity. And if you can actually implant these things into the cellular membrane, you should be able to get enough sensitivity. But one issue, again, is implementing these guys into the cellular membrane. Because you see, you need a large electric field in order to have a sizable Stark effect. Quantum Stark effect is a weak effect. So you need a very large electric field. So you have to put these guys into the membrane. And that's a little bit tough. These guys themselves are relatively small, but still it's very difficult to put these guys in there. And overall, whichever optical method you use, this is the bottleneck you are going to run. And I'm going to neglect this term. This is something to do with the available fraction of the molecules radiating, something to do with fluorescence. So let's assume the ideal scenario. This is one. The number of, the signal to noise ratio will be square root of number of photons detected times the signal itself, right? If my signal is changing 10%, right, and then I have a sizable number of photons, I can detect that. If my signal is changing 0.01%, right, if I have huge amount of photons, I can detect that. as well. But my signal is changing 100%, but I have few photons coming. That's not going to be, a large signal to noise ratio. And actually people get this genetically coded voltage indicators with very large delta S. Almost 80% is reported. But the photon counts are so small, you cannot get high signal to noise ratio measurements. The problem is inverse for these quantum dots. You have a sizable, NS, in other words, number of photons, larger cross section, no photo bleaching problems. But then you end up having this, low delta SS because electric field has to be very large to have a sizable signal change. So we come up with an alternative solution. And we use basically this nano antenna concepts. Basically, Nadir developed these concepts in early 20s. And that is the time, I moved from, I did my PhD in nanoelectronics. I moved from nanoelectronics to nanophotonics. And one of the first talks I listened was Nadir's talk. And he talked about, how you can actually find analogs of the existing RLC circuits in the optical domain. And he demonstrated that, you can actually generate analogs of RF antenna using slightly modified concepts, and a material that is made out of two metals and a gap that is, loaded with some dielectric material will be identical to a dipole antenna that is attached to a load. You see, at the time, and being honest, I thought, this nano antenna concepts wasn't actually such revolutionary because people have been doing plasmonics for quite some time. Maybe a good mathematical way to put it, but it's still plasmonics. But you see, when you name something slightly different and use a different approach, that actually opens up different possibilities. You start thinking, in different ways. Basically, one thing that we started to do for this particular research is to adapt these concepts that Nadir developed, and actually that thinking process, obviously, is based on the fact that, we have these radio antennas. We can tune their resonances. You can use different frequency radio antenna by tuning the load. So what we started thinking is, if we want to measure electrophysiological signals, we just need a load that is sensitive to the electrophysiological signals. Antenna doesn't have to be itself sensitive to it. It's just a load. And, when Nadir actually put these concepts out there, there were a lot of, work on this thing. One of the works that I read, at the time when I started and still remember is basically, they showed, the concepts that, Nadir put was actually valid. In, experimental, they verify that you can actually vary the gap. Initially, they start with a single antenna structure, no gap, and they started to, edge away using a focused ion beam tool. They can actually change the dielectric to metal ratio within the gap. And doing that, they were able to change the loading, obviously, and they can actually see it matches perfectly with the theoretical approach. So these are though not, not real-time antennas. These are not dynamic antennas. These are static. You have to do fabricate things. And there were a lot of studies about static antennas. And more recently, active plasmonic devices becoming popular. But I haven't seen any active plasmonic antenna device focused on electrophysiology. People have been doing this for display technologies and such. But what we decided, we actually, based on these concepts, right, the thinking process is basically, okay, you know what, you just need an electrochromic polymer. We know that electrochromic polymers are sensitive to electrical signals. Basically, electrochromic means electrochromatic, right? Basically, the light behavior or its optical properties changes with electric field. So if I can couple my nanoresonator with a electrochromic material, I actually have now a tunable load that reacts to the local electric field dynamics, which is actually a slowly moving field. And I have this resonator that actually couples the electromagnetic field, which is oscillating in hundreds of terahertz. So now I can couple these slow oscillations with the high rate oscillations. So this is a basic idea. And we choose P.PSS because it's known to have strong and reversible electrochromic properties. It's stable down to 10 nanometers. It's used in supercapacitors as a high capacitance. That is an important thing. And it is used in microelectrode arrays for decades. And people develop chemistries so make it biocompatible. They can be functionalized with molecules to grow things on them. Cells don't grow on everything. And there were actually some studies. This is associated to MEA literature. People actually show you can do electropolarization, you can do lithographic patterning, not at the nanoscale, and that will become important down the road. But they say at least using photolithography, they can do at the micrometer scale. And they actually show these properties from 500 to 2000 nanometer wavelength range. That is very important because you see this fluorescence, quantum dot, or the molecules themselves, they work in the visible wavelength range, maybe get close to near IR, but mostly in the visible range. And that is actually not very good because biological objects absorb light significantly in that wavelength range. Versus when you go above 1100 nanometers, you are in the biological transparent window. People actually show if you were to use like 13 or 1400 nanometer light, you can image everything in a mouse brain. So you can just penetrate through it from different sides and access all every corners of the mouse brain using light. So obviously, you want to do things in the longer run. I'm going to show you in a visible range, but you can actually do these things in the longer wavelengths too if you want to do in vivo measurements. And this technology actually is PSS, extensively used in microelectrode arrays. So in a way, it will be advantageous for us to use the existing technology that is known to be biocompatible. Now, there is a problem with this electrochromic polymers, though. In order to have a large amount of modulation, you have to have a thick film because these are transparent materials mostly, right? So in order to have a large modulation, you have to have a thick film. And when you have a thick film, the way that these things work, ions are going in and out, they are doping it. Obviously, this diffusion constant for ions is a relatively small constant. And if you actually have a longer length, a thicker film, you are going to have temporal response problems. It is going to be very, very slow response. So these two things actually seems to be two competing factors, right? Whether you require a large temporal resolution, so you need a large modulation, then it has to be slow. If you want it to be fast, then it's going to have a weaker response. So those two things are actually competing with each other. Actually, these electrochromic polymers used in electronic ink applications, and at some point these were popular before the tablets. And if you recall, if you have one or seen one, the screen refreshes at a very slow rate, and that's actually one of the problems with typical electronic ink materials. And you have a similar problem with this electro-optic modulators based on electrochromic polymers. But you see, the match between plasmonics and electrochromic materials is actually made in heaven. I tell this concept, and I will show you not only in this particular example and the ones that I talked down the road, is basically, you see, you use a nano antenna, and we are using this because it's our reporter and the P dot is our load. But one advantage of using nano antenna is that it also focuses light to this tiny dimension, right? And in this case, you can see that it's way smaller than the diffraction limit of light. These are FDTD simulations. And you have this enormous field enhancement. So it actually improves the light matter interaction at a very small volume. I mean, there's no point having P dot thicker than this, tens of nanometers or 10 nanometer, right? And because the light is already focused within the P dot structure. So it actually provides a significant, light focusing into the P dot. So it provides actually electro-optic effect, a stronger one. Obviously, it's not going to be as strong as if you were to have, tens of microns or hundreds of micrometer length, but it actually, hundreds of micrometer length, but it obviously provides actually a pretty good electro-optic signal. And the way this antenna works is something like this. Before it's doped, it has a certain frequency. Once it's basically become de-doped, the frequency shifts, and you just look at the scattering signal. Obviously, this is not driving a circuit. You are not going to have a terahertz circuit, so you cannot electronically detect it. You detect it optically, and as I told you, it's actually advantageous because then you do not actually have any wiring problems. So this is the basic concept behind these structures. Let me continue my talk with I'm a little bit behind the schedule, but let me continue with my talk with the fabrication. I usually don't talk about fabrication. It's going to be short, but it's important because we discovered a couple of important things related to behavior of these structures. And I'll continue with sensitivity measurements, discuss about temporal response, optospectrochemical measurements, and finish up with large area millionplex recording measurements. So the way we actually make these devices is, using basic lift-off approaches. In this case, we use electron beam lithography. Most recently, we started using actually deep UV large area fabrication. We can fabricate these things now on wafer scale. But once you actually generate your antenna, you coat them with PDAT. You realize that's the easiest way to do it, and scalable way to do it, and a cost-efficient way to do it. So you use this galvanostatic approach. We worked on it a little bit. Now we can actually deposit 5 nanometers at a time in a reliable fashion and coat the thicknesses that we want. So this is a little bit tricky though, just to coat the gold, because just to give you an idea, this is an ITO coated glass substrate. So this is a conducting substrate. Obviously, in order to coat this gold, you have to apply an electric field, and you have this ITO, which is conducting. You want to coat the gold, but not the ITO. So we developed a selective scheme, which I will touch briefly, that wasn't shown before, but that help us basically coat only these nano antennas. And you see the middle in the middle here. It looks like it's it's like a eggs, yellow region, and you have the yolk around it. That's actually PDAT structure. Now, when we are doing these studies too, we also wanted to understand obviously the temporal response, and in order to do that, we try to understand the interface between a gold and a gold PDAT electrode with the solution, because basically the overall the circuit behavior of this is identical to a large or a small one. So we start doing this electro impedance spectroscopy measurements, try to project basically that interface into an electrochemical circuit. This is not the RF circuit I showed you earlier with the load. This is an electrochemical circuit. And the PDAT capacitance here connects those two circuits to each other. You have the electrochemical circuit and you have the electromagnetic circuit. So the capacitance of the PDAT is varying, and that variation actually helps you, translate the signal from electrophysiological to electromagnetic. And you can actually get a pretty good estimate of the features here. And what we realize is basically with the changing thickness, the response times drop significantly. And there were a number of studies in the literature. People show things on the millisecond. And with this kind of thicknesses, we achieved actually microsecond, sub-millisecond measurements. People actually don't look at this kind of thicknesses because, in order to have a strong electro-optic effect, you often look at, some micrometers of thick films. And the other thing we realize is basically, one of the basic limitations of this capacitor is basically charging time. Like any interface, you're going to have RC limitations, right? And capacitance is proportional with the area or area, right? So when you look at actually RC time, it turns out basically it's proportional with the area. And it gets better as you make these things smaller. It's not exactly proportional with area, but the capacitance is affected by a couple of other factors. But it's proportional with the area more or less, and you end up getting basically a temporal response time that improves as you thin the PDAT and as you actually make it smaller surface area. So then actually these antennas are beautiful because they're extremely small and they focus light. So you can actually make your PDAT thinner for the reasons I told you earlier. Now, there are little dots on the surface. And if I just coat those guys, not connect these polymers with each other, then I have this perfectly small cross-section and very thin load that can respond variations at a high rate. And we tested basically some fabrication conditions. This is a CV cyclic voltammeter measurement, and we can actually determine where is the nucleation point, when the PDAT starts to electropolymerize on different materials. And we show that there is a window, a potential window, where you can actually deposit PDAT just on the gold structures. If you are below that window, there is no electropolymerization. Above that window, you have everything coated. In between this window, we achieved basically a controllable deposition of PDAT and show that we can deposit as thin as 10 nanometers without problem. In very small areas corresponding to some 100 zeptoliters of material. This is extremely small, obviously. Then the next thing we started to do actually look at how sensitive our antennas to the field. And these electric fields actually, if you look at literature, people often refer voltages, because when you use MEA, you have a counter electrode and you have a working one, you look at the potential difference in between. We are measuring electric fields, so I have to report things in terms of electric field. But just to give you an idea, this is way smaller than the electric fields in the cellular membrane. In cellular membrane, this should be 10 to the power 6 to 10 to the power 7 volt per centimeter. So we are in like 1,000-fold less than that. And that value is actually often accepted as extracellular values. These are basically controlled measurements. I'm changing the electric field. So what we did basically, we compare our loaded antenna with the uncoated bare gold antenna structures to understand the effect of the loading. And we show that, you know, the improvement is 3 orders of magnitude. There were actually a few people working on this gold nano-antenna for electrophysiological measurements. There were a handful of work before us, but they weren't using this loading mechanism. And, you know, they weren't able to detect signals from cells, but they showed, you know, electric field sensitivity. Now, when we actually coded with PDAT, you know, using loading effects, we show that we can improve delta SS, the signal part in this, SSNR ratio equation, 3 orders of magnitude. And when you look at basically the variations in signal, and these are actually well quantified for quantum dot probes. So you see with the quantum dot, you observe like 11% change in, intensity, but you have to apply 10 to the power 5 volt per centimeter electric field. Cross sections are bigger than, molecules, but they are 4 orders of magnitude at least smaller than our cross sections. And, we are using 3 orders of magnitude less electric field, and we are getting comparable, variations. Obviously, I have to pick this data from another person's literature. I don't have the exact numbers, but, it kind of gives you an idea how large the SSNR ratio in our case. So these are, quantum dot literature. And one nice thing about it, actually, I forgot to mention one nice thing. This is a linear relationship. It varies linearly with the electric field, which is very good, which means you can actually quantify, the electric field strength. We did some analysis. I don't want to get into the details of this. We compare, a normal antenna versus PDAT coded structure. We showed that the improvement is inversely proportional with the number of electrons at the Fermi level, and that gives us a number 3.66 10 to the power 3. And the experimental values are getting to this are very close. That's like 3.25 10 to the power 3. And one thing we understand is conducting substrate ITO is not critical at all. We use ITO just to code, PDAT using galvanostatic method. ITO is not important at all. You can literally make colloidal structures and just send them into the tissue, and you should be able to actually monitor the signal directly by looking the scattered light from this spherical symmetric objects. Basically, we look at SSNR ratios, with pristine versus our electroplasmonic antenna, basically electrochromic plasmonic antenna. That's the shortened version. So we compare those two, and it turns out basically, a single nano antenna, electroplasmonic nano antenna, can give you 100 to 200 SSNR ratio. That's remarkable because these are smaller than the diffraction limit of light. So you can actually detect signal from single nano antenna with high signal to noise ratios without all these limitations that people run into who uses optical methods to detect electrophysiological signatures. And you can see why actually previous attempts to use just the plasmonic gold nano antenna didn't work, because SSNR ratio is significantly small. Obviously, if you have a bunch of antennas, you might be able to detect a signal, but when you look at actually single antennas, you won't be able to resolve this small feature, so you will not be able to detect subcellular behavior. So you have to take large area measurements. Now, these are our initial measurements. So these are controlled, varying electric field is applied, and we demonstrated that, optical response times less than 200 microseconds. So that's like, 500 kilohertz signals, which is pretty good. That's all you need to be able to detect electrophysiological signals. And again, these measurements might be actually limited with our instrumentation. Obviously, this number, I'm not exactly sure if this is the limit. This is the upper limit, I would say, not the bottom limit. And we show that our structures actually work million cycles without any problem. We can actually run these things for quite some time. Now that brings us to, somehow my slide actually froze. Okay, that brings us to this optical field measurements. So these are one of our earliest measurements using dark field setup. A simple optical microscope, an inverted microscope, not a laser light like people use this for fluorescence dyes, a simple halogen light source. You shine light. Basically, everything you use are the standard instrumentation that comes with an optical invert microscope, and then we monitor the the light intensity using a handheld spectrometer. I'm talking about something about size of my hand. We show that we can actually detect using very low intensity light. We can actually, this is like 3 orders of lower than the typical ones used for genetically encoded voltage indicators. So this is actually significantly lower than using this, simple setup, incoherent light source and handheld spectrometer. We show that we can do large area measurements, and this was actually published about a year ago in Science Advances. I recommend taking a look at it. Very comprehensive paper, very detailed. We detailed everything with that. So that other people can replicate our results. But most recently, we moved from this to whole area measurements using imaging. The initial measurements was, using handheld spectrometer and, taking an aerial measurement. So we moved from that. Obviously, we know that our structures enables us to resolve, individual antennas. So we actually moved from that to large area measurements. This actually shows you, a 2.2 millimeter to 2.1 millimeter area. It's way larger than anything you will find from an MEA electrode array. And, we are measuring single antennas here. At least, the resolution is limited by the pixel sizes in our CCDs. And it showed us that, we can actually achieve a measurement capability that's 22 million simultaneous measurements at a time. And you can actually see, how the signal propagates through a cell. I don't have the video easily available right now, but, if you look at the video, you see this thing actually beating. Slightly different patterns, but it beats with time. That's basically what you expect. These are cardiac cells. You expect them to generate this electrophysiological signal and slowly moving. Now, we did a trick here because cardiac cells obviously can also move, right? So we basically cancel their movement using some chemicals. So they're just basically spiking this electrophysiological signal. So, and we show that basically, we can detect subcellular resolution measurements over large areas. So I like to thank my students who did this work and my collaborator at Notre Dame University and National Science Foundation mainly, and Moore Foundation and their support, and also other agencies supporting our research in multiple ways. I can take your questions.